Hi, welcome to physics lesson. Today we go to chapter 5.3, application of electromagnetic induction. Electromagnetic induction has many applications. 1. Generator. Generator is an energy converter that converts other form of energy into electrical energy. It involves induced current. Do you remember you have learned induced current? Induced current will be produced if there is a change in magnetic field through the coil. Okay, so we simply make the coil to be rotated in the magnetic field, so we can have induced current. Other type is a shake torch. Maybe you can shake the magnets inside the coil, so the coil will experience a magnetic field change. So we can also find induced current. Maybe we take a look on the shake torch.
This torch has its own generator. When we shake the torch, the magnet moves in and out of the coil. This induces a voltage to charge up the battery. It is claimed that a 1-minute shaking allows the torch to work for 10 minutes.
Okay. So we want to study about the induced EMF and induced current in a rotating coil. The first step is to rotate the coil inside the magnetic field. So you have learned in the last chapter that is Fleming's right-hand rule. Okay, so if the wire is here, AB, okay, moving up, you will cut through magnetic field lines, so we can have induced current. Okay, and the movement of the wires going up, so the form points up, B field from north to south, so first finger point to the right hand side, so you can have an induced current which is into paper. Now suppose we have an observer eye here, okay? So AB induced current flow into paper, and if we consider the wire CD, the wire is moving down, so the form points downward. Okay, B field right hand side again, so the current, induced current will flow out from the paper that is out of paper. Okay, so induced current here. Okay, so for the deflection of galvanometer, you will point to the net as current flow to the net. Okay, and for drawing the coil, we would like to draw like this. Okay, AB here. Okay, to represent this wire, and also CD here to represent wire CD. So here we find that in this current is for the wire AB will be into paper, okay, and off paper for CD. Okay, so this is the first step to make a generator. Now we have induced current. For the step 2, what happened? Okay, like you know, the magnetic field lines will point to the right hand side, which is horizontal. Horizontal parallel field lines. If the wire AB move to the right hand side, do you think it cut through magnetic field lines? The answer is no, okay? If the wires move to the right hand side horizontally, so it won't cut through magnetic field lines. So we find that low induced current flow. Okay, similarly, the YCD move to the left. It won't cut full B field lines. Low induced current. Okay, so this is an important finding. You find that if the coil is vertical, we say this the coil vertical, low induced current. Okay, step 3. The coils keep rotating, so it would cut full magnetic field lines again. So we can have induced current, but now the induced current will flow in the opposite direction. Why? By right-hand rule, the wire AB now is going down. Okay? So the induced current will be reversed. Okay, compared to step 1, YAB going up. Now step 3, YAB going down. So we have opposite direction of induced current. Okay, but this is not a successful generator. Do you know why? Because we found problem here at point E. That is, the wire would get twisted. Okay, so we have to solve this problem in order to have produce a generator. Okay, simple DC generator. We can solve the problem by using slap ring. In the DSC, you can use full ring if you forgot the name. Okay, but I will suggest you please remember slip ring. Okay, slip ring means ring can be rotated with the coil. Okay, so wires will not be get twisted in this case. It can rotate with the coil. Okay, and always touch the carbon brush. Carbon brush enhance contact. Okay, now we can have an induced current all the time. But we have to memorize the coil orientation. As we have taught before, if the coil is in the horizontal direction like this wire move upward, so it cut through magnetic field lines most rapidly. Okay, this wire moving downward also cut through magnetic field lines most rapidly. Okay, so we would have a maximum induced current in this case. Okay, if the coil is horizontal, maximum induced current. If the coil is vertical, what happens? The wire move to the right hand side at this moment, so it won't cut through magnetic field lines. So if the coil is vertical, low induced current. Okay, so similarly we can find the induced current for one revolution of the coil. Okay, so it will be a sine wave here. Actually, it's a cosine wave. Okay, we call this a sinusoidal wave. After we can make a generator successfully, we want to study how to increase the induced EMF and induced current. We have a hidden equation. Induced EMF equal to NBA omega. Okay, so there are 5 ways to increase the induced EMF and induced current. Induced current, we go to IR. Okay, if we can increase induced EMF for same resistance, we can also increase induced current. So there are 5 cases to increase induced EMF and current. We use stronger magnets, increase B field, more number of turns of coil, increase the area within the magnetic field. Without, if we do not mention within the magnetic field, that means the coil may not be inside the magnetic field, so there will be no magnetic flux change. So actually we need to mention the coil should be within the magnetic field. Also, winding the coil on a soft iron core, that is increase the B field passing through the coil because it can enhance the magnetic field. Okay, rotating a coil at a higher speed, that is and high omega. Example 9. Now you see the AC produced by AC generator change with time. So what is the frequency of the AC? Frequency. Now, so you have you memorized the coil orientation? Zero current, that means the coil is vertical. Okay. Horizontal here, vertical, horizontal, vertical. So what happened? That's one period, okay? One period is 0.04. So we know period is 0.04 second. Frequency equal to 1 over T. That is 25 Hertz. Okay, part B. And if the coil is rotating twice, that means double omega. What happened to the frequency? Like you know the equation for circular motion, T equal to 2 pi for omega. If omega is double, so the period will be half, okay? Half period. So period will become 0.02 second. So the frequency will be double, 50 Hertz. Okay, and what is the change in maximum current? Now we know equation, heating equation, and you don't need to prove this equation by yourself. Okay, it will be OC, MB omega. Okay, double omega. So we have double induced EMF, and we have double induced current. Okay, so that will be the answer. We can have a DC generator by using commutator to replace slip ring. Okay, commutator. Now you should remember the function of commutator. Commutator is it can change direction of current every half turn of coils. Okay, it changes the direction of current every half turn coil, so we can have DC. Okay, direct current. So the opposite side of current will be reversed. So this is one period. Okay. Practical generator. Okay, now first is bicycle dynamos. We rotate permanent magnet instead of rotating a coil. You can avoid the circuit making connection via moving contact. Maybe moving contact would make spark, or the lifetime of bicycle dynamo would not be too long. Okay, like here, the coil is fixed with a rotating magnet, permanent magnet. The coil experience varying, that means changing, varying magnetic field. Okay, so we can have induced EMF and induced current for closed circuit. Okay, and for the power station, we use rotating electromagnet. We don't use permanent magnets in this case. Chapter 5. I hope you can have a try by yourself. Chapter 5. And this is the answers. Okay. We go to point 2, eddy currents. Eddy current, experiment 5E would have 2 parts. One is to use the aluminum ring, and we will use aluminum ring with slit. Second is we will use aluminum plate, and also aluminum plate with slots. Okay, maybe we look at the video first.
We will study the effects of eddy current induced in a piece of metal when the metal is placed in a changing magnetic field or moves in a magnetic field. We will study the effects of eddy current induced in a piece of metal when the metal is placed in a changing magnetic field or moves in a magnetic field. Put a coil of 1,100 turns round the bottom of an iron stand and insert an aluminium ring on the top of the coil. Connect the coil to a DC power supply. Switch on the power supply. What happens to the aluminium ring? Now use an AC power supply. What happens to the aluminium ring? Repeat the experiment with an aluminium ring with a slit. Use the DC power supply, then the AC power supply. What happens to the aluminium ring in each case? Next, we will see what happens when a piece of metal moves in a magnetic field. Suspend an aluminium plate so that it can swing freely about its pivot. Place the plate between 2 slab-shaped magnets with unlike poles facing each other. Pull the aluminium plate to one side and then release it. What happens to the aluminium plate? Repeat with an aluminium plate with slots. What happens to the aluminium plate this time?
The first part is we use aluminum ring, and we find that the aluminum ring will jump for using DC, and will flow in air for if we use AC. Okay, no jumping if we use aluminum ring with slit. Okay, and for this, aluminum plate would swing. Okay, swing. If we put a magnet in between the aluminum plate, the aluminum plate would come to stop very fast in a very short time. Okay, but if we use aluminum plate with slot, it will not come to stop in a very short time. Okay, do you know why? Now maybe we look at the reason behind. Like if we have a solenoid like this, okay. Now suppose the current flow in this direction. So the B field by right hand grip rule, the B field is going up. Okay, in order to oppose the magnetic field change, for the inside the magnetic plate, we have induced current by Lenz's law. Okay, so the current will be induced in this direction to oppose the B field coming into the magnetic to the metal plate. Okay, now so here we find eddy current, induced current. You have learned this in chapter 5.2. But if we use a changing, we use AC, then we will have a changing magnetic field. So we would have a continuous eddy current. Okay, it flow all the time by opposing the magnetic field change. We have a long time induced current and long time opposing force. Okay, so that's why aluminum wing can flow in air if you use AC because of changing magnetic field and also changing the opposing force, okay, all the time. However, if we use DC, the aluminum wing will only jump one time when we switch on the power supply. Okay, do you know why? Now here, if you consider the metal plate to be a wing, okay, if we have induced current like this in this direction, so here, south pole here. So in order to oppose the south pole should be induced at the bottom of the wing. So we can have induced current, which is in this direction. Okay, so we can see there will be an opposing force by like poles repel here. Okay, but if we use AC, that means we only switch on or off the current. Okay, and the current only in one direction, flow in one direction. Okay, so it would not produce a changing magnetic field. So if we consider the wing, the magnetic flux before we switch on the power supply, it will be zero. Low magnetic flux through the wing. After we turn the power supply on, so magnetic field will pass through the wing, so it become BA. Okay, if there is a magnetic flux change, we have induced current, and we have one opposing force. Okay, but there will be no change for the magnetic flux change, so only we have one opposing force one time. Okay, only one opposing force. After we switch it off, it becomes zero, so there will be a magnetic flux change. However, there will be no repulsion, okay, because no magnetic field is generated by the solenoid if the current is zero. Okay, so in this case for DC, we can only find the aluminum wing jump one time. That's when we switch on the power supply. For the AC, we always have changing magnetic field, so we have so we have a continuous eddy current and continuous opposing force, so it can flow in air. Okay. How about second case? Swinging an aluminum plate. Okay, now here you see aluminum plate would cut through magnetic field lines. Okay, so we can have induced current which oppose the motion of the plate by Lenz's law. Okay, so there will be a braking force. However, if we use aluminum ring with slot. Where is it? Aluminum ring with slot. So it will be a low resistance path. Okay. Sorry. Maybe we draw like this. Okay. Aluminum ring, aluminum plate with slot. So the current will be small. The induced current will be small compared to the original one. Okay, so less induced current we can find with an aluminum plate with slot. Okay, so less braking force will be produced. Right now we go to and take a look on the examples for the practical use of eddy current. The first one is induction cooker. For the induction cooker, maybe we take a look on the video first.
We are going to show the working principle of the induction cooker. A coil is placed on a retort stand. It is connected to an AC power supply. Put an aluminium ring through the stand and rest it on the coil. Switch on the AC power supply. Why does the ring float in mid-air? If we press the ring towards the coil, the ring will get warm very rapidly. This is due to the induced currents flowing within the ring. Such currents are called eddy currents. The same principle is applied in induction cookers. The induction cooker heats up the metal pot without any flame. It merely uses the heating effect of the current. Metal cookware should be used for an induction cooker. If a glass beaker is used instead, the water will not be heated. Why?
Okay, for the induction cookers, induction cooker use coils of wires with a high frequency AC. That means you can set up a very fast changing magnetic field. Okay, if we put a metal cookware above the induction cooker, you would experience a large eddy current. So large eddy current would have a large heating effect. We can cook food by conduction. Okay. However, we cannot use an insulating pot. Okay, for the induction cookers. Okay, otherwise, no induced current will flow in the insulator. And Part B, eddy current breaks. They are similar to experiment 5E. You know with eddy current we can have opposing force, so we can have a braking force. Okay, for a moving conductor inside a magnetic field. So here it's similar to swing aluminum plates between magnetic poles. Okay, we can have a magnetic brake here. Yes, an advantage, which is there will be no direct contact between brakes and the objects. Okay, so noise and mechanical wear can be reduced. That means we can use for a longer lifetime and also a less noise pollution. We can find this in roller coaster. And also we can find this in a higher speed train. Okay, you can see the wheel has a short mallet. Okay, That means we can have induced current to stop the roller coaster or high-speed train. We can also use this for cooking. There is induction furnaces. Other applications, moving coil microscope. Okay, there is a microphone. Oh, moving coil microphone. Okay, moving coil microphone. Okay, if not microscope. Okay, if we talk here. What happened? So tired. Okay, if we talk. Okay, now we know it will be a longitudinal wave. That means the vibration is along to the direction of travel of the wave. Okay, you would make the diaphragm to move up and down. Okay, if the diaphragm is connected to the coil will be moved up and down. Okay, and you see here we have a cylindrical magnets inside. So if the coil move up and down, you will cut through magnetic field lines. Then we have induced current. For the induced current signal, we can use loudspeaker to broadcast the sound. Okay, so this is the working principle for moving coil microphone. The vibration of air causes the diaphragm to vibrate. The coil move up and down. So we have induced AC. Okay, by using this AC, we can amplify the AC and then convert back to sound by using loudspeaker. You have learned loudspeaker in chapter 4. Okay, that is if you have current B field, then you can have force to make the diaphragm to make the sound again. Digital pens is the application for electromagnetic induction. For the pen, you have coils. Okay, and then for the sensor plate, we have varying magnetic field. Okay, because current is connected through the coils through the sensor board. Okay, if the pen experience a changing magnetic field, it would have an induced current. Okay, so by reading the current, we would know that's the location of the digital pen. Okay, and also the digital pen does not need any power source because it can get the energy by electromagnetic induction. Okay, so the position of the tip of the pen can be detected and sent back to the computer. Another example is a hard disk. Now you see there will be a hard disk head here with right head. Okay, if we have a current flow for the for this right hand, it can magnetize the magnetic material inside the hard disk. Okay, maybe it can make a good alignment of the magnetic material inside. Okay, now say if I magnetize the magnet, okay, this part and that part no magnetize happen. Another part magnetize again. Okay, this is the writing process. Okay, so for the reading process, there is to move the coil. That means move this head. Okay, maybe from left to right. Move this coil to the right. So you can read the signal in the hard disk. Now, if the coil move in this direction, so we find magnetic field passing through the coils. There will be an induced EMF. Okay, another part. Also, we have induced EMF. Another part with also induced EMF. Okay, because like with B field here, low B field, and B field here. Okay, so we can read the message 101010 from the hard disk. Okay, now this is the writing, this is the reading process. We have to magnetize the plater. Okay, after magnetize the plater, we can write the information for the inside the hard disk. Okay, we can also move the head, so we have induced AC signal. So that is the reading process. Checkpoint 6. Okay, have a good try for checkpoint 6. This is the answers. Okay, everyday physics. Actually, with many applications of electromagnetic induction. One is a metal detector. Okay, do you know why? Now, metal detector actually it consists of a coil connected to AC source, produce a changing magnetic field. Okay, if the detector come closer to a metal, the changing field would induce a current in the metal object. Then the magnetic field of the induced current would affect the original field that triggered the alarm. Okay, now maybe detector here, sending changing B field. Okay, if there is a metal here, so we find induced current to oppose the B field, right? So if the coil where measure a change in the magnetic field, so it will trigger the alarm. So this can be used for making a metal detector. And also, second example, octopus car. Octopus car has its own coil pattern. Okay, if the card machine send a varying magnetic field, it can induce the coil in the octopus card. So so you can see there is no battery for the octopus car, and we can have a signal through passing through the octopus car machine. Now, this is the end of chapter 5.3. Wow, very long. Maybe you can check the answers after you have tried the practice. Or you can download the PDF in eCards. I will show all the answer to you. I will suggest you to try all the MC questions, because this is to use to check your concept of electromagnetic induction. Okay, don't miss any past paper. Question 32 is a very good example for Shik torch. Okay, have a try, and this is the answers. Okay, don't look at the answer before you have done it. Self-test. Okay, self-test answer. Well, you can find solution of your textbook here or download the PDF. Oh, it will be the end. Okay,